Hi everyone, I hope you're doing well. Today we're going to continue our discussion on chemical kinetics. So first, we're going to go over 3 techniques that are commonly used to monitor a reaction mixture. So those techniques are polarimetry, spectroscopy, and pressure measurement. So let's start with polarimetry. Polarimetry measures the change in the degree of rotation of plane polarized light caused by one of the components of your reaction over time. So as an example, a long time ago, a scientist was measuring the rate of reaction for the decomposition of sucrose into glucose and fructose. Now, sucrose can rotate light in a clockwise manner, and glucose and fructose rotate light in a counterclockwise manner. Now, this is similar to how some sunglasses work. They actually rotate light, and that helps to dim the intensity of the light coming into your eyes. So if we can measure the degree of rotation of a sample over time, we can determine how much product is produced versus how much of the reactant is left over. And this will give us our change in concentration over time, and that's our rate of reaction. Another way to monitor a reaction is using the pressure of the reaction. So remember that the total pressure of a gas mixture is stoichiometrically related to partial pressures of the gases in the reaction. Now this relates to Le Chatelier's principle as well, because remember we can push a reaction in either direction, towards the reactants or towards the products, just based on how many moles of gas are present. So you could adjust, for instance, the volume of a cylinder that contains a mixture and manipulate the reaction that way. Now, in terms of measuring the rate of reaction, you can measure the total pressure of a mixture of gases over time. And depending on that change in pressure, you can kind of backtrack and figure out, do I have more reactants or do I have more products? Probably the most common method that's used is spectrophotometry. And we've used this method in our class before, not necessarily to measure reaction rate, but to measure the concentration of product that's forming. But you can use this to measure the concentration of product over time. So remember, spectrophotometry measures the amount of light of a particular wavelength that's absorbed by one component over time. So down below we have a little diagram showing how this works. We have a light source, and that is passed through a prism, which separates all of the wavelengths of light. And then we use one of those wavelengths and pass it through our sample. And then, depending on how much light passes through the sample, we're going to detect the intensity of that sample. And we can do this continuously over the time of a reaction. So, for instance, let's say that our product has a red color. And what we'll do is pass the complementary color through the sample. If the sample absorbs a lot of that color, we can then measure the resulting intensity and get a graph of the intensity over time, which relates to the concentration of the product over time. And then from that, we can determine the rate of the reaction. Another way that we can keep track of a reaction over time is by taking tiny samples from the reaction mixture at different time points. Those samples are called aliquots, and when we take these aliquots, we then pass them through an instrument which can then measure the concentration of a particular component of the reaction. So, for example, let's say you have a sample or a reaction that's occurring in a beaker, and at time 1 you take, let's say, 5 milliliters, or it's probably even smaller than that. Usually aliquots are in the nanoliter range, but just for the sake of the example. And then what we would do is run that 5 milliliters of sample through an instrument, or maybe we would perform a titration to determine the concentration of our product. And then let's say at time 2 we take another 5 milliliters and we determine the concentration at that time. And then we just keep doing that for however long we need to determine the rate of the reaction. Now, one instrument that's really useful for this type of analysis is gas chromatography. Gas chromatography can measure the concentrations of multiple components in a mixture. However, you do need a sample that is very volatile, so that means it can easily evaporate. And we also have to separate all of the components in the mixture. Otherwise, we'll just be detecting all of the components at once. So this diagram shows kind of a simplified version of how a gas chromatography instrument works. So usually you have your aliquot that's injected into the gas chromatography device. And here we have a column, and this column is going to separate all of the different components. And the different components are usually in their gaseous state as they're passing through the column. Although sometimes you can pass things through their liquid state, there's also liquid chromatography. And essentially what happens is, well, using different methods, you can separate those different components. So either they travel really quickly through the column or really slowly. That's one way to separate them. Or you can also separate components based on how well they stick to a surface. And then eventually, once you've separated out each of those different components, you can measure their concentration using this device. And what you get is what's called a chromatogram. So you can see there's 2 peaks in our chromatogram, and each peak corresponds to a different component of a mixture. And then we can determine the concentration of the mixture or of each component. And then we can determine over time how that concentration is changing, and that will give us our rate of reaction. So there are a lot of different ways that we can determine the rate of a reaction or measure it using different devices. Now, there are some factors that affect reaction rate, and one of those is reactant concentration. So rate does depend on the concentration of one or more of the reactant molecules. So what we can do is form what's called a rate law. And this is an equation that relates the concentration of reactants to the rate of the reaction. But this is only for situations where the reverse reaction is negligible. So we're not going to see equilibrium here. So it would be something like this where we have a single arrow going to our products. And if there is a reverse reaction, it's very, very tiny and it's, completely negligible. So if we can relate the reaction or the reactant concentration to the rate law will look like this. So this is for a reaction where we have one reactant and it's becoming different products. So we would write rate equals K times the concentration of the reactant A raised to a power. And that power is given the symbol N. So N is called the order of the reaction. And this is an integer usually that determines the rate dependence on reactant concentration. So we'll talk a little bit more about that in a second if it doesn't quite make sense yet. And then K is the rate constant. And we'll also talk more about that later as well. Now, if you have multiple reactants, so let's say A plus B and they're becoming products, then we would write that the rate is equal to K times the concentration of A raised to a power times the concentration of B raised to a different power, or they might have the same power, it depends. So again, those orders of the reactants, those might not be whole integers all the time. You could have B raised to the power of 0.5 or 0.75, something like that. But most often we'll see, a power of 1 or 2 or 3 or something like that. So let's talk a little bit more about reaction order. So that exponent on each reactant in the rate law, again, is called the order with respect to that reactant. And then the sum of the exponents is called the order of the reaction. So in our example where we had multiple reactants, we can add together N and M, and that will give us the order of the reaction. So there are three common orders of reaction. There's zero order, first order, and second order. So for zero order, N would equal 0. For first order, N equals 1. And second order, N equals 2. And here again, we're just assuming we have one reactant. Now, if a reaction is zero order, the rate of the reaction is always the same. So, for instance, for the reaction where A becomes different products, let's say we change the concentration of A. So let's say we double the reactant concentration. In a zero order reaction, this will have no effect on the reaction rate. So the rate will stay exactly the same. Now, if a reaction is first order, the rate is directly proportional to the reactant concentration. So if we double the initial concentration, that will double the rate of the reaction. So they're directly correlated with each other. If a reaction is second order, the rate is directly proportional to the square of the reactant concentration. So if we double A, the reactant, that will quadruple the rate of the reaction. Now, if we want to determine the order of a reaction, we do have to figure it out experimentally. So again, we would use one of the methods we saw earlier, and then we would just track the concentration over time, and we would also track how the rate or average rate is changing over time as well. So we're going to use what's called the method of initial rates. And in this method, we take data from different experiments with varying starting concentrations of reactants. And then we also determine the initial rates, but usually those are given to us. And then we'll determine how the rate of the reaction is impacted by changes in the reactant. All right, so that was a lot of words. Let's actually go over some examples. All right, so here I have 3 different experiments, and we're going to assume that in each experiment we just have one reactant and it's becoming various products. So in our first reaction, let's say that we double the concentration of the reactant. So initially our reactant concentration was 0.1 moles per liter, and we found that the initial rate was 0.015 moles per liter per second. And then we doubled the concentration of A and measured the initial rate. So the new concentration of the reactant is 0.2 moles per liter. And our measured initial rate was still 0.015 moles per liter per second. So because the initial rate didn't change, that tells us that we have a zero order reaction. So the rate is equal to a constant times the concentration of A to the exponent 0. So again, the rate of the reaction does not depend on the concentration of the reactant. Now we're going to focus on table 2 right next to it. And let's say this is for a completely different reaction, but we still just have one reactant. And let's say we again double the concentration of the reactant. And initially we find that the rate is 0.015 moles per liter per second. But after doubling the concentration of the reactant, the rate changes as well. And in fact, it becomes 0.060 moles per liter per second. So that means we've quadrupled the rate of the reaction when we double the reactant rate, concentration. So this tells us that we have a second order reaction. So the rate is equal to some constant times the concentration of A to the power of 2. All right, and then in our last example, so for a completely separate reaction where we just have one reactant again, we're going to double the reactant concentration. And again, initially our reaction rate was 0.015 moles per liter per second. And then our second reaction rate was 0.030 moles per liter per second. So the rate doubled as well. So there's a direct correlation between the reactant concentration and the initial rate, which means we have a first order reaction. So we would write that the rate is equal to a constant times the concentration of A to the power of 1. All right, so again, it is important to know, how product concentration or the rate of your reaction is affected by the concentration of the reactant. And this is true in several different scenarios. So for instance, in our own bodies, we have certain rates that things metabolize at. And if you have a really high concentration of something, and you can't quite metabolize it fast enough, that can have negative consequences. So understanding these different rates is really important. Now there is another way to determine the order of a reaction. This is more mathematical, and this is really useful if you don't have a whole integer order. So if your order is maybe 0.5 or 0.75, but we're just going to use our example from the last slide. So the equation we can use, we're going to compare two rates. So we'll just pick one rate and compare it to another rate. And then we're going to set that equal to our rate expression here. So really we're comparing those to the concentration of the reactant. So let's say this will be our second trial, this will be our first one, so we're going to compare those two sets of data. So for rate 2, we'll plug in 0.030 moles per liter per second, and we'll divide that by the first rate, which was 0.015 moles per liter per second. And then we'll set that equal to our concentrations. So the second concentration was 0.20 moles per liter, and the first concentration was 0.1 moles per liter. And these are both raised to the power of n. I'm not going to include the subscripts because that was just to indicate whether it was our first concentration or second concentration. Okay, so now we can kind of simplify this. So 0.03 divided by 0.015 is 2. And the units cancel, so we don't have to include those. And then on the right-hand side, the rate constants cancel, so K, we can get rid of that. And then we have 0.20 moles per liter over 0.10 moles per liter. And we're just simplifying this, so everything's raised to the power of n. So 2 is equal to 2 raised to the power of n. So in order to solve for n, which is the order of the reaction, we're going to take the log of both sides. Now remember, if you have the logarithm of something raised to a power, we can bring that power down in front of the logarithm. So let's do that. Let's see, so the log of 2 is equal to n log of 2. And then we're just going to solve for n. I'm going to move everything over. So n is equal to the log of 2 divided by the log of 2. And that's just equal to 1. So this is again another way to solve for the order of a reaction, especially if it's not so cut and dry. The examples we just went over were pretty easy to do without doing any complicated math, but occasionally you'll have a reaction where that's not the case. So this is another way to figure out that order. All right, now let's look at a few graphs to kind of visualize how the reaction rate or the concentration of a reactant can change over time. So on the left, we have reactant concentration versus time, and the concentration of the reactant is on the y-axis, and then time is on the x-axis. So you can see that for a zero-order reaction, the concentration of A is decreasing linearly over time. And then for a first-order reaction, we get more of a decay plot, so we're getting a bit of a curve there. And then for a second-order reaction, that curve is even greater because we're losing more reactant over time. And then on the right-hand side, we have rate versus reactant concentration. So the rate is on the y-axis, and the concentration of the reactant is on the x-axis. And we can see that the rate for a zero-order reaction does not change with concentration of A. So that's just a flat line. And then for a first-order reaction, there's a linear relationship. And for a second-order reaction, it's a bit of a curve. Because, again, remember, if we double the concentration of A in a second-order reaction, we're quadrupling the rate.